All right, cosmology, chapter 26. So this is, a picture of an image from Hubble, the Hubble Space Telescope, and in it, virtually everything you see is a galaxy, and they're all, red-shifted and follow, Hubble's law. All right, so what we're going to do is we're going to study the universe as a whole, like the entire universe. That's the subject of cosmology. All right, so these are the different topics we're going to cover: the large scales, the expanding universe, what's going to happen to the universe. Will it go on to continue to expand forever, or maybe it'll collapse down on itself? What is the geometry of space? And some of these ideas, by the way, with especially like the geometry of space, it uses. To really go into it requires a level of understanding of Einstein's theory of general relativity, which is quite complicated mathematically, and we're just going to touch the surface of that anyhow, so to speak. We'll talk about curved space. What's the fate of the universe? Will it keep expanding? And then we'll talk about this relatively new discovery. It was discovered around the year 2000, and its effects, the dark energy's effects on cosmology. And then, of course, we'll reintroduce this idea that started back with Einstein, and it turned out Einstein used this for the wrong reasons, although nowadays people are looking back at it and saying, well, perhaps it's describing dark energy. Anyhow, and we'll look at the evidence for cosmology. One of the big evidence, of course, is what's called the cosmic microwave background radiation. This discovery in 1964 won two guys named Penzias and Wilson the Nobel Prize in physics. All right, so let's get started. All right, so this is a picture of a survey from, remember the Sloan survey, as it's called, which is just a single telescope that's devoted to looking deep into the universe, and spending a great deal of time accumulating photons for very, very distant galaxies. Anyhow, the thing that we noticed with this big huge wedge of the sky, and we look at this wedge of the sky in different directions, we find that the largest thing out there is about 300 megaparsecs, so 300 million parsecs in size. Now, the thing about that is, some people call it the wall or the Great Wall. It's just regions where there's a whole bunch of galaxies and clusters of galaxies concentrated. Anyhow, the thing that we're interested in here is that you don't see any structures bigger than this. All right, so if we consider the Great Wall, and even the voids are about, the largest voids I think are about 100 megaparsecs. So when you get to stretches bigger than 300 megaparsecs, you don't see any overall structure. In other words, the universe will look completely the same no matter where you go, as long as you're looking at a scale greater than 300 megaparsecs. All right, and there's another survey that has been done. Sometimes this is called the pencil beam survey, as its name implies. We're just looking in a real small region of sky, as opposed to this one where it's looking at a large wedge of sky. Anyhow, this beam of sky, where let's say you're looking up above the galactic plane and then below the galactic plane, and of course you still see things like the Great Wall and the voids, but you're seeing it in a much smaller, in a smaller section of sky. Anyhow, this same type of survey, or the same similar surveys, give you the same kind of structure, that you don't see anything bigger than about 300 megaparsecs. So nothing at all. All right, so what does this imply about the universe? So basically the idea is homogeneity. Okay, so the universe is homogeneous when you look out at a scale more than 300 megaparsecs. In other words, if you so I think this is actually a really good, well, it's not really an analogy. This is a really good way to think about it. So if you take a square, so each side of the square, each of the three sides is 300 megaparsecs, which, remember, that's a huge amount of distance. But if you plop that square anywhere in the universe, and of course, the universe is much bigger than this, it'll basically appear exactly the same. All right, you're going to see voids, you're going to see walls, you're going to see filaments, you're going to, super clusters of galaxies, things like that. But no matter where you are, you'll always see the same. So that's being homogeneous. Okay, so that's the idea of the universe being homogeneous. And then also, it doesn't matter what direction you look. Okay, so if you look in any direction at all, you're going to get the same view, on a large scale. As long as you're above 300 megaparsecs, you're going to get the same view of the universe. The local galaxies will be different, of course, but overall you're seeing essentially the same thing. And so that's called being isotropic, right? So that's the same in all directions. So when we combine the idea of the universe being homogeneous, or the homogeneity and isotropy, that is also known as the cosmological principle. All right, so on really large scales, more than 300 megaparsecs, the universe is both is isotropic and is homogeneous. So and again, that's called the cosmological principle. And so this is a basic tenet of cosmology, that this is true. We've never seen violations of this when we go at large enough scale. All right, so now here's the thing. There was this guy named Obler. He was I think back in the 19th century, is when he lived. He posed a very interesting question. It's more of a philosophical question, really, but it does have actual astronomical implications that you can test. And so his idea was actually really simple. If the universe was homogeneous and isotropic and infinite and unchanging, then the basic idea is, no matter what direction you go, you'll eventually run into a star. Now, of course, the further stars are dimmer, but eventually you're going to run into a star. So you think about so you've got to imagine like an infinite universe. There are so many stars out there that in any direction you're eventually going to hit stars. And he said, well, why is the sky dark? It should never be dark. Like, if the universe is truly infinite, and everything's the same, and every direction is the same, then of course the sky shouldn't even be dark. Even because the further away you get, you're still getting more and more stars. All right, so that's called Obler's paradox. Now, of course, we can solve Obler's paradox by realizing that that the universe is not infinite and it's not unchanging. It is in fact very much finite, and it has changed. since the beginning of the universe. And in fact, we can work out, as you're about to see, the fact that the universe, we can figure out from Hubble's constant how long ago the universe began. All right, so remember, with Hubble's constant, it says the recession velocity, which is really a measurement of the redshift. Don't forget that. The astronomers like to talk about the redshift rather than the recession velocity. But for now, we'll just stick with this idea of recession velocity. Is equal to the Hubble constant, which remember is 70. The accepted value nowadays is 70 kilometers per second per megaparsec, or the average value, I guess you should say, and that's times the distance. Okay, so that's Hubble's law. And so how does this get us out of Obler's paradox, as it's called? Well, this law is actually the expansion of space itself. I know I've mentioned this before, but with cosmology, we really are going to tackle this idea. All right. So how long ago did the universe start? So here's the thing. Like, if you look at the basic idea that velocity is distance divided by time. And by the way, this is a kind of a simplistic view, as we're going to find out a little bit later. The universe has not been expanding in a constant manner. In fact, it was a very big surprise in the year 2000, or right around the year 2000, that the universe was not accelerating, or I'm sorry, was accelerating. In fact, in the distant past. All right. Anyhow, so let's just assume that the velocity is distance divided by time. We rearrange the equation. We get time as distance divided by velocity. But if we replace the velocity here with this, we think about it in terms of the precession velocity, which is h0, Hubble's constant times the distance. Then notice the distance cancels, and so you just get units of 1 over the Hubble constant. And so 1 over the Hubble constant, so you have to change the units of everything. In other words, you got to get kilometers, you got to get, basically turn the megaparsecs into kilometers, which, remember, those are 2 units of distance. And so 1 over h0 is the age of the universe in seconds. At least in this simplistic model, that's exactly what it turns out to be. And so if you work it out, it's about, so the value for just using h without any other considerations for right now turns out to be about 14 billion years, which, by the way, is not too far off the accepted value of 13.8 billion years. And we'll see how we get to that number in a little bit. All right. Now, here's the other thing about Hubble's law that we need to understand, is it's not dependent on any one particular galaxy. All galaxies would see Hubble's law. In other words, if they look out into the universe, every galaxy is going to be redshifted over. So let's look at these different situations. Okay, so here are 3 different situations. If you're in somehow you're in galaxy 3 here, so this is galaxy 3. You look out and you look in all directions, but you look out 100 megaparsecs in one direction, you get a recession velocity of 7,000 kilometers per second. If you look out in the opposite direction, you get the same thing, right? And then you look twice the distance, so 200 megaparsecs. It's the expansion. Sorry, galaxies are receding twice as fast, right? And see, the thing is that it doesn't depend on whether you're in galaxy 3 or like, let's say you're in galaxy 2. That's the second situation, right? Galaxy 2 would see exactly the same situation. They look over here, and they see a galaxy 100 megaparsecs away, and it has a recession velocity of 7,000, and then